Welcome back to the Explainer. Today, we're taking the real and reactive power concepts from Part 1 and turning them into the power triangle. This is the ultimate tool for power factor correction, driving multi-million-dollar capacitor bank decisions out there on the grid. Let's get right into it. Okay, so just a real quick recap to set the stage. Complex power, which we call S, is split into two totally distinct pieces. First, you've got P. That's your real power. It's the stuff doing the actual physical work in your system. And then you have Q, the reactive power. Now, Q doesn't do any real work. It basically just magnetizes your equipment. You know, things like your induction motors and transformers. It's power that just gets borrowed and returned, back and forth every single cycle. So, when you put P and Q together, you get the power triangle. And this is where things get really interesting, because it lets us calculate the power factor, or PF. Mathematically, it's just the cosine of the angle theta, which you find by dividing your real power, P, by your total apparent power, S. Now, why is this equation absolutely crucial? Well, think about it. A perfect power factor of 1.0 means literally all your current is doing actual productive work. But say you've got a power factor of 0.7. That means 30% of your apparent power is just reactive overhead. It's essentially dead weight. And the problem is that dead weight draws heavily on the utility and can seriously overheat your feeder cables without actually accomplishing anything. But there's a brilliantly simple fix. By installing a capacitor bank right in parallel with your load, you're introducing leading reactive power into the system. And here's the magic. That leading power neatly cancels out the lagging reactive power drawn by all those inductive loads we just talked about. So your overall apparent power, S, actually shrinks, all while your real power, P, stays exactly the same. It's a real game changer. You are literally taking the load off the grid. You're transforming a strained, overheated feeder into something that runs highly efficiently. Now, to actually wield this tool mathematically out in the field, you're going to use this specific correction formula. It tells you exactly how many kVAR of correction capacitance, that's our QC, you need to add to the system. You just take your real power, P, and multiply it by the difference between the tangents of your current angle and your target angle. It's just right-angle trigonometry, really, but it gives you a precise way to figure out how to drop your reactive power draw from the grid without touching the real power at all. Just as a quick example, say a plant draws 1,000 kilowatt at a 0.75 lagging power factor. By plugging those numbers in, you'd find you need roughly 542 kVAR of capacitance to hit a much safer 0.95. You add exactly that, and boom, your system is remarkably more efficient. Right, so here's the really crucial point when you actually step onto a job site. You've got to know the rules the utilities enforce. See, most utilities will absolutely hammer industrial customers with heavy demand charge surcharges if your power factor drops below 0.85. They want you operating efficiently, for sure. Because of this, substation design usually targets correcting to somewhere between 0.95 and 0.98 lagging. But, and this is a massive warning here, you should never ever try to correct perfectly to 1.0. If you overcorrect and accidentally push into a leading power factor, you can cause some really dangerous voltage rises. Plus, you risk setting off resonance problems with the exact same capacitor banks you just spent a fortune installing. So don't do it. Let's actually test your field intuition a bit with a quick scenario. Imagine you're an engineer, you're monitoring a facility, and suddenly, the plant's power factor just collapses. It drops from a really healthy 0.95 down to 0.70 overnight. But here's the catch. The total load, like the actual work being done by the factory, hasn't changed one bit. So, what went wrong? Any guesses? Well, the most likely culprit? Your capacitor bank tripped offline. Whether it was a blown fuse or maybe a protective relay opened up, the plant suddenly lost all of its reactive power support. Without those capacitors doing their job, the utility had to instantly step right back in and supply all that reactive overhead again. And that causes the power factor to absolutely tank. This is a very real, very common troubleshooting pattern you're definitely going to see out in the field.
So, just look at the foundation you've built so far. You came in knowing real and reactive power existed, but now you can actually calculate power factor, size a capacitor bank to fix it, and navigate the very real penalties that utilities enforce. That is a massive tool for your engineering kit. Moving forward, we're ready to head to where the real grid actually lives, balanced three-phase circuits. But before we go, I want you to think about something. If correcting power factor on just a single line is this delicate of a balancing act, how on earth do we keep millions of watts perfectly balanced across three separate phases all at the exact same time? Well, we'll uncover exactly how that works in our next explainer. See you then.